could actually then imagine that you could have a civilization of travelers. Basically, they would be space-time nomads. So you would have a nomadic civilization where all they do is travel from place to place and meet up in certain star systems. So as long as you chose your distances right and your accelerations right, you could actually have meetup points where, periodically you run into a few of your own kind and meet up and trade and tell stories, and then everybody takes off again. And so you could do something like that. Now that sounds like a weird lifestyle to us because we're not nomadic, but there are nomadic civilizations on Earth, so this wouldn't be so bizarre too.
My guest tonight is a physics professor at the University of Albany in New York. Dr. Kevin Knuth is a former NASA research scientist who has worked for 4 years at NASA Ames Research Center in the Intelligent Systems Division, designing artificial intelligence algorithms for astrophysical data analysis. Tonight he's here and we're going to talk about interstellar travel. That and more is coming right up on My Alien Life. My Alien Life is recorded live from atop the Northern Rocky Mountains and is available on Spotify, Stitcher, iTunes, and everywhere fine podcasts are found. My website is at www.myalienlifepodcast.com. There you will find my email address, all previously recorded shows, and more. I am Cameron Brower. This is My Alien Life, and the podcast starts right now. Dr. Kevin Knuth is in the studio tonight, and we have something in common. We both attended universities in Montana. Doctor, I believe you have a degree from Montana State. I went to the University of Montana, which makes us vicious cross-state rivals from Big Sky Country. Dr. Kevin Knuth, thank you so much for joining me, and welcome, sir.
Well, thank you very much for having me. Yeah, that's correct. I got my master's degree in physics from Montana State.
A lot of people settle in Montana after that. You didn't, though.
No, I didn't. I actually was rather sick during most of my time in graduate school, and it was a big mystery at that time. It turns out later that I suffer from, altitude sickness, and that I can't acclimatize. And so I never actually acclimatized to high altitude. So 5,000 feet is too high for me.
Yeah, you were at 5,000 feet. U of M is more around 3,600 feet. So yeah, I could understand that. It's a different type of environment for somebody who didn't grow up around there. At the open of the show, I gave a little bit of a bio about you, and I was wondering if you'd explain artificial intelligent algorithms for astrophysical data analysis, because to me it sounds like there's a lot of math involved there, right?
Oh, yeah, there's a lot of math. Basically, we are designing algorithms that use probability theory and statistics to estimate model parameters, basically. Basically, we come up with mathematical models that are describing what we're trying to quantify or study, and the algorithms use probability theory to estimate those models, figure out which models work best, basically.
Tonight, I'd like to talk a little bit about interstellar travel, if you don't mind, and as our universe becomes larger, literally and figuratively. Of course, we want to find out what's there how much do you think of our universe that we could realistically expect to explore in the next, say, 10,000 years?
10,000 years.
10,000. If we're still here in 10,000 years, how much do you think we could explore? That's a loaded question.
It depends on a lot of factors. Right now I'm working on a project where I'm actually simulating interstellar civilizations, and one of the important parameters is what I call the reach. So it's kind of a combination of the distances. Basically, it's the distance that they can basically reach through travel. So it depends on how long you're willing to sit in your spacecraft and wait for the trip, and it also depends on how fast you can go, which is a function of both your acceleration and the velocity. So you might have a ship that can accelerate very fast, but if you can't handle some of the challenges that occur greater than 30% the speed of light, you're going to run into trouble. But otherwise, you could also have a ship that doesn't accelerate very fast, but you can eventually get up to 80% the speed of light. It's going to take you a little while to get there. So there's several factors that play into that, and that seems to be the major factor that determines whether a civilization can basically visit a large number of other solar systems.
So if you and I were going to engineer a method of interstellar travel, where would you even start? I mean, where do you begin to even conceptualize that sort of activity when we've only gone about 240,000 miles with manned spacecraft?
Where would we start? Well, that's a good question. I don't know exactly where we'd start without getting horribly technical about various things. One of the biggest problems is that our spacecraft work by literally throwing stuff out the back, right? You throw stuff out the back of the spacecraft, you give it momentum, but then you have to have conservation of momentum, so your spacecraft gets momentum from that in the opposite direction. And so the difficulty is that you have to carry your fuel with you, and eventually you'll run out of fuel, and so you can't accelerate anymore once you've run out of fuel. Those are really the two of the main problems. The other difficulty is that humans can't handle arbitrarily large accelerations, so we're really limited by how fast we can actually accelerate. So getting up to high speeds will take some time. If you accelerate at 1g of acceleration, it will take some time to get there. So there's several challenges that have to be overcome, and it's not immediately obvious how to do that. Now, there are some people who have some ideas, and there's some discussion going on right now, which is a lot of fun and very interesting. But that's, at this point, that's what it is, just ideas and discussion. So we'll see. We'll see. I'm hopeful.
Yeah,
you can only do it by trying. So if you don't try, you aren't going to succeed. So I think it's that simple.
So in time travel, where speed is a variable, there's acceleration and there's deceleration, and as you mentioned, it takes a lot of time. But if speed is significant, and by that I mean a speed close to light speed or close to it, wouldn't acceleration and deceleration require kind of right now gravitational forces that would be essentially destructive to almost anything that we've engineered so far?
Well, you can accelerate at low rates. If you accelerate for half of your trip with one acceleration, you can decelerate with that same acceleration for the other half of your trip. It's symmetric. So that's one thing you could do. And let's see.
Let me ask you this realistically:
yeah.
if you're going from 0 to 95% of the speed of light, it's going to take a long time. I mean, I don't think anybody really realizes or thinks too much about how fast the speed of light is and how long it would take to get there. I mean, it could take years feasibly to get there, right? Or more.
Yeah, let's see. You can get to, if you accelerate at 1 g of acceleration, so the same acceleration that you feel from gravity, basically after something like, after about 730 days, you would be at 90% the speed of light.
Okay.
So 730 days is something like 2 years. So it would take you about 2 years to get to 90% the speed of light. But then you're going to have to slow down again. So it's going to have to, so slowing down at that same rate, you're going to have to take another 2 years to slow down if you're going to do it at 1 g of acceleration. So your trip is at least going to take 4 years just based on the acceleration alone. And of course, you can coast in between at 90% the speed of light if your spaceship can handle plowing into all the stuff out in space at 90% the speed of light, which is another big problem. So there's other challenges there.
Since you brought that up, what would that look like if you traveled for 1 light year and you passed through a portion of space that is equal to the size of the vehicle that you're in, and let's say it's 100 feet in diameter and it's perfectly circular. You're talking a lot of real estate through space as you travel through space. So what are the chances that in that portion of space that's 100 feet wide for 1 light year that you would run into something significant?
Well, you probably aren't going to hit. Well, that's a good question. We don't actually know. The thinking is you're probably not going to hit things much larger than size of a grain of sand. Now, a grain of sand coming at you at 90% the speed of light is going to do a lot of damage. So
that would be pretty amazing.
I would worry about that. Yeah, I would worry about that. But there have been some people who've done some calculations to see what kind of radiation hazards you would have and what kind of damage you'd get from micrometeorite bombardment. So basically there's a paper by Semyonov from 2009 where he does some of these calculations, and he notes that as when you get above 30% the speed of light, you're going to have a lot of hull damage from the front of the spacecraft is going to be bombarded by micrometeorites. So this is hitting all those little grains of sand or dust in interstellar space. And at 30% the speed of light, you're probably going to hit about 100 of these dust particles per square meter per second. So it's just going to very rapidly deteriorate your hull as you're just sandblasting the front of your spaceship away, right, with sand coming at you at 30% the speed of light. It would be quite awful. So
that's pretty significant. That's more than I would have thought. That's quite a bit.
Yeah, and it's surprising. It really poses a huge engineering problem. So you have the two main engineering problems are, one is how do you accelerate a craft at a constant rate and for a long period of time, without running out of fuel or having to carry all that fuel with you. That's the first engineering problem. And then the second one is basically how do you protect your spacecraft from deterioration from, basically micrometeorite bombardment at close to the speed of light, as well as from radiation. So you have some other problems because light itself, starlight, if you're flying to or toward a star system, starlight is going to be blue shifted into higher frequencies. So you'll have X-rays and gamma rays basically being, coming at you as you're racing toward this star. And then you have other problems because once you get up to about 70% the speed of light, you get just running into a hydrogen atom. You've got about one hydrogen atom per cubic meter. So hitting a hydrogen atom, basically you've got you can imagine that yourself as you're basically flying through a particle accelerator, right? So this hydrogen atom's coming at you at 70% the speed of light, and it hits an atom on the hull of your spacecraft, but this is actually going to create particles just like you do in a particle accelerator. So these would be nucleon collisions that would give you pion production. So you'd be creating particles and all sorts of things. So you get particle creation happening at, by the time you get to 70% the speed of light. And
wow. So
yeah, and so
that was gonna, I right now I thought of that absolute question. And so if you're creating particles when you're out in space, what would that look like? I mean, obviously, you have the front side of this craft that's flying at incredible speeds through space, and you're creating particles. I mean, are they going to attach themselves? Are they going to be destructive?
You're going to get photons bouncing off the front of your ship. You're going to get and you're going to have particle creation going on. So you're going to have the whole front of your ship is going to be shooting gamma rays, X-rays and gamma rays off the front of it, as you're plowing through space. So some of these, so some people have looked into this. Some of these relativistic craft should be you should be able to see some of them if they're nearby and flying that fast. So anybody flying past our solar system, you should be able to see the radiation, coming from their spacecraft, just from them plowing through space at these speeds. So
there's radiation, there's debris, any other dangers out there that we normally wouldn't think of from just normal travel like we have on Earth?
Well, the bigger problem, the other problem is that we don't really know what's all out there. So, we do know that that there are black holes around, and we don't really know how many there are and how big they are or small they are and how common they are. So if it turns out that you have a sufficiently high density of primordial black holes that formed, during the Big Bang, these things could be small. They could be a centimeter across, but you don't want to fly into a black hole a centimeter across. You're not going to see it coming, and it would do a crazy amount of damage. So that would be another danger, and that's something we don't know anything about. So
in space interstellar travel, is there such a thing as a shock wave or any other wave that craft would produce?
Yeah, you would actually get a bow shock, just like you do when you have an airplane flying through air or a boat through water. You get the same type of effect. And in fact, we have photographs from the Hubble Space Telescope of stars moving through interstellar material, and stars plowing through interstellar material actually have a bow shock around them as well. There's some nice images of that.
Because, celestial bodies out there also traveled at tremendous speeds, and we don't really think about what the consequences of a star or something else travel at those speeds. So what does that actually look like?
Yeah, well, they don't travel quite at what we would think of as relativistic speeds yet. They're still, I think, the fastest object. There's a hypervelocity star. It was found by Brown et al. In 2010, and that's going somewhere. It's around. What would that be? It would be a little less than. I guess it would be sorry, I'm taking a minute here. It looks like a little less than a tenth of a percent the speed of light. So
that's significant. That's huge.
It's significant. And then there's a hypervelocity neutron star going about the same, around that same order of magnitude. So, yeah, so it's basically.
So obviously it's important to get away from the planet and to gain this incredible speed that we would need to gain. But does fuel last a lot longer, and is it more efficient when you're out in space and you're using that fuel?
No, I don't think.
As opposed to on Earth,
exactly.
when you actually take off from Earth, you have to use a significant amount of fuel just to break Earth's gravity, its environment, its to get out into space. Once you get out into space, does that fuel become more efficient, and does it burn more effectively in order to push you out further and faster into space?
Oh, not really. The biggest problem blasting off of Earth is you've got to carry all your fuel with you. So you've basically got to lift all that fuel up with you. And so initially, most of the fuel you're burning initially is going into accelerating the rest of your fuel. And that's where you're wasting because you've got to carry the fuel with you, you're really wasting a lot of energy in that way. So
how would our fuel source be different, say, in 1,000 years from now? What would be the optimum type of fuel that we would use to get up to speed in space rather than using a combustible like we're using right now?
Oh, I don't know. If I knew, you'd be talking to a guy with a great startup company.
I thought you would have that answer. I was ready for that one. So, yeah, that's kind of an amazing concept.
I should add the correction. It looks like those hypervelocity stars were going about a 0.5% the speed of light.
Right. That's big though. That's huge for a.
That's crazy fast. Yeah.
So how did they get that fast? I mean, where did that speed come from?
I don't know exactly. I don't know. I don't know the theory behind accelerating something like that to those velocities.
So would that be part of the Big Bang? Some sort of residual effect?
No, it would have happened. It would have happened far later. So I don't know.
Wow.
Yeah, I'm not sure. I don't know the details.
Is interstellar travel, is that one-way travel? Meaning that we're going to get out there, but there's no way we're coming back?
You can come back. The problem with that is that, well, the benefit of getting up to speeds close to the speed of light is part of the benefit is, you're going fast. That helps. So you're covering a large distance in a small period of time. But the real benefit comes from the fact that at speeds close to the speed of light, you have the effect of time dilation. So an observer in the galaxy watching you fly by will see your clocks moving more slowly. So you can actually get great benefit from that and can travel much further, because your time slows down as you're traveling. That's one way to look at it. There's two ways to look at it. You can look at it as from the perspective of the traveler, and you have what's called length contraction in that case. So lengths get shorter if you're traveling at a high speed and you look at something passing you. So if I'm traveling from here to Alpha Centauri, the nearest star system, as I get close to the speed of light, the lengths contract. So basically, the distance from my perspective as a traveler, the distance from where I am currently to Alpha Centauri actually decreases. So going close to the speed of light, I actually shrink distances, which makes my trip go faster. So there's so I kind of rushed over that, and I apologize. So there's those two perspectives. So from the perspective of the traveler, distances contract, and so as long as I get going close to the speed of light, I don't have very far to travel, and that makes your trip shorter. And from the perspective of somebody in the galaxy, somebody on Earth watching the traveler take off and fly away, or someone on Alpha Centauri watching them arrive, they see the traveler's clocks is moving slowly, so time is slowed down for the traveler. So the traveler can travel vast distances with their clocks barely advancing. And those two perspectives, while they're different perspectives, the same thing happens. The same effect happens when all is said and done, and that is that the relativistic traveler basically can travel large distances rather quickly, much more quickly than than if you didn't have relativity working for you.
When you consider the fact that lengths contract, wouldn't that suggest that, being that changes, and normally we would think all things being equal, wouldn't that suggest that the speed of light could be breached and maybe you could go faster than the speed of light?
No, you can't. You can't go faster. I mean,
why?
The same theory that's telling you that lengths contract and how the lengths contract basically say that the speed of light is the speed limit. It's just the way things work. So you can think of what that really tells you is that distance and time are related to each other. So the fact that it takes time to travel a distance, is significant in the sense that times are somehow related to distances. So the speed of light turns out to be this limit where that tells you that Alpha Centauri being 4 light years away is literally 4 years away. So that there's kind of an equivalence there between distance and space.
But the faster you, is that taking into account that the faster you go, the distance also decreases?
Right. Well, the faster you go, the distance decreases. That's right. So you can actually, so for the traveler, you can travel those, what you initially measured as a greater distance, you can travel it faster. And so you're not exceeding the speed of light because that distance actually decreased. So you don't need to, you aren't going to go faster than light. And for the outside person, for the person on the outside of the spaceship watching you fly by, they just see your time slowing down. But according to them, you're still going to take, more than 4 years to get to Alpha Centauri. So.
But relatively speaking, if you're in the craft itself, it's a quicker trip, right?
For you, it's a quicker trip. Yep.
Relatively speaking, is that a reality that it's a quicker trip, or just the experience?
It is a reality. No, it is a reality that's a quicker trip. And so for you as the traveler, you get there much faster than, for you as the traveler, it would take a much shorter time. So I can give you some examples here. So if you are, right, so here, these are some cases if you're accelerating at very high rates of acceleration, which of course we wouldn't be able to withstand. So if you were accelerating at 100 times the acceleration of gravity, and you do this for half the trip, and then you decelerate at 100 times the acceleration of gravity, for the traveler who's going to spend most of their time traveling very close to the speed of light, the trip to Alpha Centauri would only take 43 days. But for people on Earth and people in Alpha Centauri watching you travel, that would take about 4.4 years. So it turns out to be a very big difference. And now if you turn around, you go, so let's say I take off to Alpha Centauri for a quick trip. For me, it's a quick trip, and I accelerate at 100 Gs of acceleration halfway and then decelerate the rest of the way. For me, it's a 43-day trip, but for you, you've seen that it's taken me 4.4 years to get there. And then now if I turn around and come back, it'll take me another 43 days, but for you, it'll take another 4.4 years. And so you'll have had about 9 years pass for my round trip to take place. But for me, it will have only been it'll be about 3 months. So we have a big difference there. And so in that sense, it's you could think of relativistic interstellar travel as being a one-way trip. Because if I go much further away, then, so another star system that we're now interested in is called Trappist One. And it has 3 Earth-like planets, or 3 planets in the habitable zone, and Earth-sized planets in the habitable zone. So those planets could have liquid water on them. And that star system is 39 light years away. So if I traveled to that star system at 100 G of acceleration, I could get there in basically 60 days from my time as the traveler. But for you, it would take me, from your perspective, it would take me 39 years to get there. So, and now I turn around and come back, and it's another 58 days for me. So I'm looking at a 116-day trip. And and you're saying, wow, you've been gone for almost 80 years. So my 60-day trip is for me is an 80-year trip for you.
So would the structure of the craft or the occupants inside ever become distorted at light speed, or would they stay the same?
They're distorted in the sense of the time dilation and length contractions that people observe when you're going fast, but when you slow down, everything goes back to normal. So, and for the traveler traveling in the spacecraft, everything is normal. So
it wouldn't affect the absolute, the molecular structure, the atomic structure of an individual or the craft at traveling at those speeds?
Yeah, no, it wouldn't affect that at all. Nope.
If a craft took off from, go ahead.
But we would have we would have a 79 and a half year difference in time.
But what about that experience, that 79-year experience? Would that actually reflect itself physically upon me as a traveler? Would I be 70 years younger than everybody that I returned to meet when I came back?
Yeah, you would be 70 years younger than everything on Earth, yeah.
So that does affect some sort of molecular and atomic level an individual or whatever went to that distance and back, right? I mean, it's different. So why is it different?
Well, the time that you experience is different than the time that people experienced on Earth because you were accelerating, and so it doesn't affect you in the sense that you're just, after a round trip like that, you're just 100 days older. So that's no big deal. That's normal. And but everybody on Earth and everything on Earth itself, well, the whole rest of the galaxy is actually 80 years advanced. So basically, what's happening is, you see, space travel is related to time travel. So if you travel fast through space, you're also traveling into the future. You can think of it that way. So traveling very fast through space is the same as traveling into the future. And the problem is you can't go backwards in time, so there's no way to reverse the effects. So if I'm going to go on a very distant trip, if I want to travel to the other side of the galaxy, I can do that. And if I accelerate fast enough or get going at a high enough speed, I could do that within, maybe a couple years. But by the time I get back to Earth, traveling across the galaxy, I've traveled on the order of 100,000 light years. So it's going to be 100,000 years in the future back on Earth, when I come back. So in that sense, it's a one-way trip. I'm basically racing into the future thousands of years.
Wow. So if a craft took off from Earth and experienced time dilation during the travel, can the craft communicate effectively or normally with Earth, via whatever communication that we use now or some other communication in the future? Can we communicate?
Well, you can. You could send out back radio waves. The problem, they would be Doppler shifted into very low frequencies, and everything would be coming at a low rate. That would be commensurate with your clock going slowly. So everybody on Earth would see your clock moving more slowly, and so everything you would do would be slowed down with respect to Earth.
So what would the interpretation of those communications look like with time dilation? Does it stretch them out? Would we have to compress those, or how would we understand what those communications mean once they've been altered?
Oh, they would be stretched out. So that everything would be stretched out and slowed down.
Does gravity bend radio waves and light, or stretch both out?
Gravity would, yeah.
I'm sorry. What about
Yeah,
time dilation? Does that have an effect on
the time
waves?
dilation affects everything as well. Yep.
Wow.
Yeah.
So what would be the most likely method of interstellar travel of an advanced civilization whose maybe their technology is vastly exceeds our own even in the future, but of course they would still have the laws of speed of light, right?
Yeah. So if you were, so I call that a relativistic traveler rather than a faster than light traveler.
Correct.
So, which is hypothetical. So at this point, but a relativistic traveler, yeah, would have to. Well, the biggest problem is the time dilation again. The time dilation works for you if you want to travel. It doesn't. It works against you if you want to come home. So you really have to give up on this idea of coming home. So there's a few things you can do. One is you can, just deal with it and leave and not come back. So you just go be an explorer and take off and go see what you can see. And you're not going to come back and tell anyone about it. You can send messages back, but that's it. You could go colonize another world. And so you could do that. You're not coming back home, so you don't worry about the time differences again. That's another possibility. And then the last one that I've been able to think of is you could actually, if you were careful and you did some planning, you could meet up with friends as long as your friends were also traveling. So let's say we made a plan that I'm going to fly off to Trappist One, which is 39 light years away, and you're going to go to another star system, Gliese 667c or something, to that planet, and you head off that way. That's a 25 light year trip. Mine's a 39 light year trip, and so we choose our speeds such that we both travel off, and then we come back. And if we pick our accelerations correctly and the speeds correctly, we can come back to Earth at the same time. Now, of course, when we do get back, it's going to be, something like 80 plus years in the future. But for you and me, it'll only be a couple months. So we can come back and we can, share, compare notes, do what you need to do, and then you can go on again. So you could actually then imagine that you could have a civilization of travelers. Basically, they would be space-time nomads. So you would have a nomadic civilization where all they do is travel from place to place and meet up in certain star systems. So as long as you chose your distances right and your accelerations right, you could actually have meetup points where, periodically you run into a few of your own kind and meet up and trade and tell stories, and then everybody takes off again. And so you could do something like that. Now that sounds like a weird lifestyle to us because we're not nomadic, but there are nomadic civilizations on Earth, so this wouldn't be so bizarre to a civilization like that.
One of the things I throw out there from time to time is my thoughts, and being that it would make so much sense to have a nomadic type of organism out there that is very, very adept at interstellar travel and is able to travel and with no consequences, meaning that they have nothing to come home to. They have nothing other than travel in their future. So I don't know why that we have such a hard time absorbing that concept. Don't you think that it would be more possible or more likely to have somebody or something out there traveling through space and time with a total disregard to getting back to some some destination A is where they started out with. I mean, instead of just heading towards Z, wherever that may be.
Right. I mean, humans are wanderers, so I mean, we
don't wander far, though. We don't get far, yeah.
But we've colonized the whole planet. So there are people who do this, and so I can see in the future, once we have spacecraft that can go fast enough, there will be people who just take off and go and do. Maybe some of them will be clever enough to set up some kind of plan so they become like nomadic and can maintain a society, and others you might just get others taking off to be rogue explorers. I'm just going to go see what I can find, and that's it. So you could imagine, those different scenarios like that.
And wouldn't the craft capable of interstellar travel need more than one type of propulsion? For example, we have lots and lots of people who are listening right now who believe that we've been visited by organisms from other planets. And for instance, how would a craft navigate, through years and light years through space, and then all of a sudden come to Earth and be able to navigate through the atmosphere of Earth? Wouldn't we need more than one type of propulsion?
I mean, certainly with the way we do things now, one would think so. If we look at some of the recent cases, especially the Nimitz encounters that the U.S. Navy had with the Nimitz carrier group off the coast of California in 2004, where they had the Tic Tac UFOs. Those things are traveling through air and also into the ocean, and it's not clear that they had no obvious means of propulsion, so we don't know how the propulsion worked in those cases, and it's not clear that the propulsion mechanisms were different, because we don't have any evidence for what the propulsion mechanisms were. We don't have any evidence that they were different in the case when they were in water or air. So it's not clear that you would need to do that if you were doing things differently. This is going to depend a lot on your technology, and that could be an interesting advance.
So obviously there's some sort of object that's traveling through the atmosphere, and it's traveling through liquid, possibly traveling through space. Would it mean that those things like hydrogen and oxygen and different molecular structures don't mean anything to travel? Even though they could be a barrier right there in front of you. Does that even make sense, what I'm saying?
Yeah, I know what you're saying. Yeah, well, there's a lot of problems with what we would conceive of or perceive as problems with what these Tic Tac objects were observed to do. So, according to Kevin Day, who was the radar operator on the USS Princeton, he said that the ballistic missile defense guys with their radar were actually picking these things up in low Earth orbit before they dropped down to about 80,000 feet when they would come on his radar. And so if that's correct, then basically you have these objects traveling both in space and in air, and they were also picked up on sonar when they would drop into the ocean. So you have them also operating in water, and the speeds that they would have had to be traveling in air, given some of the data that we have, are up to about Mach 60, so 60 times the speed of sound. So that's a really crazy. Those are crazy speeds. So
yeah. And not even approaching the speed of light, so it's still
right. Yeah. So moving through air at Mach 60. I mean, Mach 1 you should be having sonic booms.
Right.
Moving through at Mach 60 is you should have far worse happening. And so Mach 60 is basically about 45,000 miles an hour, which our fastest spacecraft is the New Horizons probe, which is going about 35,000 miles an hour. So this Tic Tac UFO was actually is inferred to have gone based on its motions. In one case, or several cases, Kevin Day on radar on the USS Princeton was observing these things dropping from 28,000 feet to sea level in 0.78 seconds, and the accelerations that you would have to use to do this would be on the order of about 5,000 Gs of acceleration. And at the midpoint, the thing, if the thing accelerated halfway and then decelerated the second half, that would give you a minimal estimate for the acceleration, which would be on the order of 5,000 Gs. But during the midpoint, the speed is on the order of about Mach 60, or about 45,000 miles an hour. So you would have much worse than a sonic boom in these cases, and you can estimate what some of these energies should be. And the F-18s are about 15 tons in weight, and these Tic Tac UFOs were about the same size as the F-18s. So even if you lowball their mass just to get an estimate of the energy. So let's just say it weighed 1 ton. So 1 ton Tic Tac accelerating at 5,000 Gs is, through that maneuver, is going to have a power of about, about 13 gigawatts, I think I computed in that case.
So if we take, for example, something that we're...
It's the same amount of power.
Exactly.
Or sorry, it's about 11. No, I'm sorry, I'm off. It's 11,000 gigawatts, or 1,100 gigawatts, 1,100 gigawatts. Yeah, it's a big difference. So about 1,000 gigawatts.
So if we take something that we're used to seeing and that we know by example, and by that I mean the space shuttle, when that enters our upper atmosphere and is capable of, if it didn't have the heat shield underneath it, would burst into flames. So what's the speed of that like? And in that upper atmosphere, there's a lot less friction than at sea level, right?
Right. So the space shuttle coming in is, coming in from low Earth orbit, where we typically operate. You're coming in at about 17,000 miles an hour, and this Tic Tac UFO was at one point observed to be going about 46,000 miles an hour. So you're basically you're more than double that.
So 17,000 miles an hour is nothing.
Yeah, no.
Except when you're a human being and going 17,000 miles an hour in some ceramic tiles and some metal, steel, and foam.
Right.
A lot different.
Yeah. Well, and the power that would be required to do that is on the order of 1,000 gigawatts, and so that exceeds the total nuclear power production of the United States by more than a factor of 10. The largest nuclear power plant in the United States is the Palo Verde Nuclear Generating System in Arizona, and that provides about 3 gigawatts of power for 4 million people.
Wow. So
this Tic Tac UFO exhibited about at least 1,000 gigawatts. It's crazy, and I can see why. You have, as a scientist or an engineer, looking at this and hearing the reports or the statements made by the radar operators, they say this can't possibly be right because we can't imagine this. It's literally that far out. And then the bigger problem is is not making a sonic boom. They're basically moving through air and water as if the air and water isn't there. And so that's very strange. Just the amount of energy that should be deposited as the thing comes to a stop is really is on the order of basically an atomic bomb blowing up. So you would have you would expect to see you would expect to see a lot more than a sonic boom in these cases. Yeah, so basically if you computed the energy that you'd have to, the kinetic energy of the object, if it weighed 1 ton, if it would have to, come to a sudden stop at sea level, that's basically 4 times 10 to the 11th joules, that's assuming a mass of 1,000 kilograms. So this is equal to about 100 tons of TNT, or the yield of 200 Tomahawk cruise missiles blowing up in 3/4 of a second.
200?
So you should have been 200 Tomahawk cruise missiles in that 1 second, in that one maneuver.
Incredible.
That was just one maneuver.
Yeah.
And so, things should have been blowing up. There should be explosions all over the place, and there's not. And that's really mind-boggling.
And nothing that we know of could survive that acceleration, period.
No, not at all. No.
Yeah.
The humans can't, humans can't withstand more than 25 Gs they can't handle 25 Gs for more than about 0.2 of a second.
But even if you had a solid block of titanium out there, it would disintegrate.
Yeah, well, the new F-35 fighter jet has structural integrity up to about 13.5 Gs. Missiles can handle a little more accelerations than an aircraft. Missiles can usually have airframes capable of standing about 50 Gs, and they can be maneuverable up to about 35 Gs of acceleration. So, but this Tic Tac object was accelerating about 5,000 Gs. So you're looking at 2 orders of magnitude greater, 100 times greater than, what our missiles are capable of doing.
So there's a lot of different theories out there, and most of them a lot of different theories for time travel and traveling to other dimensions, etc. And they're usually not formulated by somebody with the degree and the training that you've had. But is there any way that you have ever heard, or that any theory that you ever heard, that there's a way to manipulate gravity for interstellar travel?
Yeah,
or could it happen? Would it be important?
There are some ideas that one could do this using general relativity, which is a theory of gravity. So there's a theory that you could create what's called an Alcubierre drive, which basically stretches space-time out behind the craft and then compresses space-time in front of it. So it basically pulls the craft along. So basically you're stretching space-time rather than actually accelerating the craft. You can think of it that way. So there is a theory like this. The problem with theories like that are stretching space-time is you're going to need a negative energy density to pull that off. And so that's not going to be possible because we don't know how to create negative energy at this point. So we don't actually know how to do that. There have been some suggestions that, maybe we're not thinking about relativity correctly, and maybe this aspect of the theory should be changed a little bit, or that aspect, and then you could do, amazing things. But I think at this point that's just supposition. And there's not been any experiments done to confirm it, and scientifically you have to confirm things by experiment. It's nice to come up with a theory, but that's all it is a theory. Theories can be very good when you have data to back them up, but we don't have any data to back any of this up. So at this point, other than something like the Alcubierre drive, which we believe would be possible if you had negative energy, we don't have that, so we wouldn't know how to engineer something like that. And other than that, it's really just at the level of supposition at this point.
Let's talk about just for the sake of other listeners out there who want me to get into this. Let's talk about if we had an element, perhaps it was named element 115.
115?
Yes.
Oh, that's a good number.
And as far as we know, this doesn't exist in nature. Just the existence of it alone. Let's talk about that for a minute. Is it even possible for that to exist in the universe, in a universe that we know of at this moment?
Well, as far as I know, it does. Element 115, which is what, Moscovium? Is that what the name is?
Let's say existing in abundance, where it's harvestable, or you could gather it,
right.
In some sort of.
You wouldn't expect that because it doesn't have stable isotopes.
Right.
So.
What about extreme pressures of outer space, extreme conditions? In extreme conditions that we would know of currently with let me say this again, in extreme conditions that we would know of, period, could it exist?
No, I can't see how it would be possible. Physical conditions don't affect whether isotopes are stable, so that's not going to change the situation. It's not going to change the fact that there are no stable isotopes.
So when you talk about isotopes, is there a limit if you had an element of how many different isotopes there could be? Because, people have theorized on this one that there's possibly an isotope that exists in the atmosphere of Earth. Even if that's possible, wouldn't it be extremely rare and extremely dangerous?
I don't know about being rare or dangerous, but there could be isotopes of this element of 115 or Moscovium that we haven't discovered yet. That's possible. I don't know what the details are and what's been worked out with this element and what they know about it, what they don't know about it at this point. But as far as I know, the known isotopes aren't stable. So
explain really quick about what's the difference between an element and its isotope, and how are they different? And throw that at me and explain it.
Right. So Moscovium has atomic number of 115. So basically, it means that the nucleus has 115 protons in the nucleus. So the nucleus, so the center of the atom, is called the nucleus, and that's made of protons and neutrons. And the protons are positively charged. And so element 115 would have 115 protons in the nucleus. And then to be electrically neutral, so you've got an atom, you'll have to have 115 electrons buzzing around the protons, around that nucleus. Now, typically you have about the same number of protons as neutrons, at least for the smaller elements in the nucleus, but you can have different numbers. So we also often hear about carbon isotopes and carbon dating. And so you have carbon-12 carbon-12 has 6 protons and 6 electrons, and it also has 6 neutrons. So you've got 6 protons and 6 neutrons. So carbon-12 has 12 particles, or 12 protons and neutrons, or nucleons in the nucleus. However, you can have if you have an extra neutron, it doesn't change the fact that it's carbon. The fact that it's carbon is dictated by the fact of how many protons it has and how many electrons then are buzzing around it. So if you add a neutron to the nucleus, you'll still have 6 electrons buzzing around. But now we'll call that carbon-13 because you have 6 protons and 7 neutrons in the nucleus. Carbon-14 has 6 protons and 8 neutrons in the nucleus. So there are different isotopes like this.
So everything we know of the universe, it's basically made of like 92 different elements. Plutonium is something that we've had to synthesize. Should we be creating elements? What can we learn from creating elements that don't exist naturally on Earth, and what are the dangers?
We typically don't create elements in large numbers or large amounts other than plutonium. So, and the danger, of course, with plutonium is that it's both poisonous and radioactive. So that's those are two dangers that you can have. And I guess those are basically the things that you have to worry about when you create an element.
So when you're creating an element with a greater atomic number, does that increase does it increase radioactivity as one?
Yeah, you always have a chance of radioactivity, and so that some of that can come from. It depends on whether those isotopes are stable or not. If the isotopes aren't stable, then they're going to decay, and they'll decay by emitting some particles, and so we call that radioactivity. So the fact that the isotopes aren't stable means that they're radioactive.
But if you had an isotope, so if you created element 115 and it only existed with a few, just not even a second, much less than a second, wouldn't you assume that the ability for that element to have an isotope would even be less likely than creating the element itself?
Can you say that again?
If you were able to create in the lab or in a collider element 115, the likelihood that element 115 would have an isotope would be a lot less likely than creating that element itself, because in order to have an isotope, wouldn't that element 115 have to exist on its own in some environment?
No, not necessarily. An isotope means that, the word itself means basically same type. So, right. So it means that it has the same, the chemistry of something depends only on what the electrons do, because basically chemical bonds are related to sharing electrons. And the number of electrons you have is equal to the number of protons you have. So the thing is electrically neutral, because protons are positively charged and electrons are negatively charged. So, element 115 has 115 electrons. And now the different isotopes are related to whatever numbers of neutrons you happen to have. So the atomic mass of 115, apparently two of the common isotopes are one's 288 and the other's 287. So you're looking at, for 288, you've got 115 protons, and you've got 100 and, just doing math here while I'm talking, which isn't easy, which isn't fun. 173 neutrons. So you've got 173 neutrons and 115 protons. But then 287, a different isotope, would have 172 neutrons instead of 173 neutrons. And so that's basically the difference really is just in how many neutrons the two atoms have.
Statistically,
we call them both one element 115 because they both have 115 protons and 115 right. electrons, and so chemically they don't behave differently. One's just heavier than the other because it's got more stuff in it.
When we talk about two different things, we'll talk about an element and we talk about gravity. Is there any relationship between the two that one comes from the other? Can you get gravity from an element? And that's To me, that's a
Not
stupid
obviously.
question.
I mean,
but
no, it's not. It's not a stupid question, but it's not obvious that gravity is caused by an object's mass. So technically, this little atom has a mass and has some gravity associated with it, but the gravity is related to just how much stuff is there. So it's nothing interesting about that. Now, the problem is that we don't have any theory that relates gravity to the other forces. So the other forces being the electromagnetic force, which is what you usually are dealing with when you deal with chemistry. So element A element A compared to element B, they're different because they have different electric charges in the outer. They have different numbers of electrons. So while they're both electrically neutral, the electrons, one may have an extra electron that's a little more free than the others to do something. And that's basically what gives you some of the type of effects that give you chemistry. But because we don't have a theory that relates gravity to electromagnetism, there's no way for the element number to obviously do anything interesting with gravity. So one wouldn't expect one element to have any more effect on gravity than another.
So if you measured a distance from the center of the Earth and 100 billion miles in every single direction, in that space, and let's say it was a gigantic cube shape, is there more gravity, or is there more lack of gravity? Is there more non-gravity out there? And I am going somewhere with this. It's just not a very good way to put that question. But is gravity common, or is it really, really uncommon?
Oh, gravity's everywhere. I mean, gravity basically goes off to infinity because
But if you took the mass of planets and stars out of the picture, is there going to be gravity there?
Oh, if you don't have any mass around, no. The gravity is caused by mass. Yeah, gravity is caused by mass, and the gravity from an object like the Earth technically extends off to infinity. Now, the truth is it decreases with the square of the distance. So if I double the distance, it's 4 times less powerful. If I 10 times the distance, it's 100 times less powerful. So by the time I get out to infinity, it's basically zero. But it doesn't go to zero. It doesn't drop off before you get to infinity. So there's the gravity of everything is felt all over.
But if you're
it's very small if you're far away.
If you're on the Earth and you make the statement, you can make a statement, I'm on the Earth and the Earth has gravity. And if you made the statement, I'm on the Earth and the Earth has a lack of no gravity, are they the same statement? I mean, just because you're on Earth, are you experiencing gravity because there's a lack of no gravity? I mean, which comes first, no gravity or gravity?
I'm not sure how to answer that. I'm sorry.
I'm just, yeah. So, okay. Well, let's switch gears a little bit.
Yeah. I mean, the idea is that if there's mass around, you have gravity because of that mass.
Right.
And if there's no mass around, then it depends how far we want to go. If you want to consider the whole universe, then we've got to talk about cosmology, which isn't my forte. But if you keep things local, then without any masses around, space-time is basically flat, which you say there's no gravity. So that's basically it.
That's incredible. So if I said that I had a 223 gram triangle of an isotope of element 115 in a bell jar with some dry ice, taking into consideration of how incredible unstable element 115 is, would you consider my statement remotely possible or impossible?
No, considering that Yeah, the half-lives are way too short to be able to have that.
I probably couldn't run around with a triangle of element 115 isotope in a jar. And why dry ice? That's an actual statement, and I've heard it. I just
right. Yeah. So Moscovium 290 or 115 with an atomic mass of 290 is the most stable, and it lasts for about. Half-life is about 650 milliseconds.
Right.
So you're talking a little more than half a second. It's about 0.6 seconds. So if you hand me, basically that means if you hand me, how many grams did you start with? Did you claim?
223 gram triangle.
Right. So you've got a 223 gram triangle, and you hand it to me. In 0.6 seconds, it's going to be a 123. So basically 111 and a half or whatever grams, a little more than 100 gram triangle in 0.6 seconds.
Yeah, but when I hand it to you, doctor, it's in dry ice. Does that make a difference?
Yeah, the dry ice won't make a difference at all. No.
Okay.
You weren't going to affect temperatures, going to affect whether something decays or not.
So what about a statement that if I was able to have that somehow, that triangle, and I expose it to radiation, it would produce an anti-gravitational field or a gravitational field. Are there any elements that we know of when you expose them to radiation that they produce anything so unusual as gravity or anti-gravity?
You'd have to specify. I mean, first, no. The answer is no, but I would actually want the question to be more precise. What kind of radiation? Because there's different kinds of radiation.
You're right. That's unfair. That's not even a fair question.
Well, that's okay because whatever kind of radiation you tell me, the answer is still going to be no. So so that's it. So I can't answer the question without having more detail.
It's good to think about.
Although I'll say that I would expect that somebody who knew what they were talking about wouldn't just say exposed to radiation. They would say what kind of radiation.
Did you know that probably that theory has been produced before by somebody, but in 1961 that was a very common theory nationwide, that there was an element out there that we could take and expose it to radiation, and we could get anti-gravity, or we could basically float. And that the person who came up with that was Walt Disney. And if you ever saw the movie The Absent-Minded Professor, they had flubber. You expose that to radiation, and you could do it. So that's I'm thinking that's where that came from, but I'm not. Flubber. That's interesting. And yeah, you could do a lot with flubber. Flubber was way more versatile and way safer than element 15. You can handle it with your bare hands.
Fred McMurray was in that film, right?
Absolutely.
Yeah, that was a fun movie.
It was great. So you and I we did grow up at the same time. So you saw that, and I saw that. So I was.
What is flubber? Flubber is what? Is it 120 or 122? I'm just joking. And see, the trick
we're way up above 130 at that time.
So here's the thing: I've basically picked a number that's just a little bigger than 118, which is the last discovered element.
Yeah.
And 5 years from now, somebody's going to discover 120 or 122, and then somebody else can point back and say, "Oh yeah, Professor Knuth mentioned that was called flubber back in 2019 or whatever year it is now," and so it's a fun game you can play.
So, can we produce gravity or anti-gravity? I mean,
no. We don't have any idea of how to produce that other than using mass and energy. So
amazing. Do you just sit by yourself sometimes and just are so thankful at this job you have and how mind-blowing it actually is?
Yes, very often.
It's incredible.
No, it is mind-blowing, and I love my job, and I love doing this type of work, and I love working on some of these problems. I do some theoretical physics work, and it's really it is a lot of fun to sit and think about these problems and issues and think how else could we think about gravity? Maybe how could gravity be related to the other forces, and how could we show this? And then if it is, what could you do with that? Could you actually create gravitational fields, and which would be fantastic. So,
well, my guest tonight in the studio has thankfully been Professor Kevin Knuth. Kevin, before we go, I'd like you to give our listeners a final word. Where are you going to be? What can you tell them about our future, and where would you like us to be in 10,000 years?
How many years?
You don't have to limit yourself to that. Just give them the final word. I would love to have you blow my mind one more time tonight. Thank you.
Wow. I'm used to people asking me what I'm going to be doing in 10 years, and I have trouble answering that question. So 10,000. Oh God. Well, I think we need to keep trying, and we keep trying to push our science forward and see what we can do and see what we can learn. I think that's very exciting. I'm very excited by the fact that we're getting back into space. I'm looking forward to the Artemis missions to the moon. That will be fun to see happen again. I was 4 years old during the moon landing, and I remember it. I remember it quite clearly, mainly because I had all the adults in my room telling me that this was the most important thing that ever happened. And so I do remember the moon landings, the Apollo landings, but I would like to see the Artemis missions. And I'm also hoping to see the first Mars colony. I'm hoping that Elon Musk and SpaceX can pull together a Mars colony, although I'm worried that it won't succeed, but the first one very well might fail, but I think I look forward to the time when there is a Mars colony, and I tell my astronomy students, I tell them that their grandchildren will probably look up at the moon and see city lights on the moon. So I would love to see that myself. Where will we be in the future? I don't know. I imagine that we will eventually colonize the solar system. Whether we make it out to the nearest stars or not, I would like to think that we could figure out a way to do that, but with the current technology, it doesn't appear to be possible. So we have to learn more. And
so until then, let's keep trying.
Let's keep trying. And then, we have these weird tic-tac things and the other objects that the Navy is dealing with, and I think we should study them. As scientists, we should certainly study them. And in addition, it appears to be a national security issue, and maybe more. So it's potentially a huge discovery, and we should study them and find out what they are, where they come from, what they're doing, and how they work. Very simple. That idea is very simple, but I think it'll be very powerful in the long run.
I think so as well. Let's keep trying. Dr. Kevin Knuth, thank you so much.
All right, thank you.
My Alien Life Podcast.
You can find my website at www.myalienlifepodcast.com, and please subscribe to my latest downloads at iTunes, Spotify, Stitcher, and at podbean.com. And please follow me and like me on Facebook and Twitter. My Alien Life is written and produced for broadcast at Studio 254 in the Northern Rocky Mountains. The music you are hearing is produced and created by ELEON. You can find all ELEON's work online at Heart Dance Records.